The mystery of whether there is an undiscovered planet at the edge of our solar system is one that has gripped the imagination of astronomers since the start of this year. Dubbed Planet 9 by some, the world was predicted by two Caltech astronomers in January, based on the peculiar clustering of 6 previously known objects that orbit beyond Neptune. Now more evidence has been published suggesting the hypothetical world is responsible for the strange orbits of these distant objects. An increasing number of distant icy rocks have been found past Neptune, the last known official planet of the solar system, including Eris, which was discovered in 2005 by the Caltech team and was the death blow for Pluto's planetary status due to its larger size. Among these trans-Neptunian ice worlds are a growing number like Setna and L91, whose distorted orbits take them far out from the Sun, in a place called the Kuiper Belt, taking thousands of years to make a single pass. Renu Malhotra, a professor of planetary sciences at the University of Arizona, and his team looked at these Kuiper Belt objects. They found the 4 with the longest known orbital periods revolve around the Sun in patterns most readily explained by the presence of a hypothetical planet 9, approximately 10 times the mass of Earth. Professor Malhotra presented the results at the 48th meeting of the Division for Planetary Sciences of the American Astronomical Society in Pasadena, California. According to the researchers' calculations, such a hypothetical planet would complete one orbit around the Sun about every 17,000 years. At its farthest point from our central star, it would be more than 660 astronomical units, with 1 AU being the average distance between the Earth and the Sun, around 92 million miles. We analyzed the data of these most distant Kuiper Belt objects, Professor Malhotra said, and noticed something peculiar, suggesting they were in some kind of resonances with an unseen planet. In the new paper, Professor Malhotra along with co-authors Catherine Vogt and Shanyu Wang pointed out peculiarities of the orbits of the extreme KBOs that have been unnoticed until now. They found the orbital period ratios of these objects are close to ratios of 2 small whole numbers. An example of this would be 1 KBO traveling around the Sun once while another takes twice as long or 4 times as long, for example, but not 2.7 times as long. According to the authors, this kind of ratio could arise most naturally if the extreme KBO's orbital periods were in small whole number ratios with a massive planet, which would help to stabilize their highly elliptical orbits. Another paper published earlier this year presented the results of numerical simulations providing a range of possibilities for the mass and orbit for such a hypothetical planet, which could account for the observed clustering of EKBO orbits. Our paper provides more specific estimates for the mass and orbit that this planet would have and, more importantly, constraints on its current position within its orbit. Professor Malhotra said. The authors added their results should not be considered as proof that Planet 9 exists yet. The KBOs have such long orbits that they may appear unusual for some time during their orbit, and they have not been observed for long enough to get a full understanding of the forces at play yet.